Good morning, everyone, and good part of the day for those who watch this video after. I'm very happy to participate to contribute to this course of Jean Dalibard at Collège de France, and I thank him for inviting me. I'm going to talk about a theoretical proposal that we came up with Bezalel Bazak, who is now in Hebrew University in Jerusalem, on a theoretical proposal on the realization of p-wave interacting two-dimensional fermionic particles. And I think that, the proposal is 3 years old, but at the time I accepted this invitation, it was not that old. Anyway, it has not been realized, so I will keep talking about it until it is realized. And I also think that it's well in line with the course of Jean, and it's probably a nice link between the scattering theory and a few body problem and the many body world. So the motivation to study this came from the many body world. Namely, we're interested in realizing a topological px plus IPY superfluid in the spinless Fermi gas. So this phenomenon is believed to exhibit, this system is believed to exhibit a number of peculiar features related to broken chiral symmetry, and it's believed to exhibit Majorana modes, and it's also believed to allow for at least some topologically protected operations needed for the quantum computing. In fact, this system has been observed in helium-3. This is the A phase of helium-3. I show you the PT phase diagram of helium-3 here. And this is the relatively small part of the phase diagram at, note that the temperature is 3 orders of magnitude lower than the degeneracy temperature of helium, and at relatively high pressure close to the solidification threshold. This helium-3 is not the system that we're interested in because it has, there is an interplay between orbital degrees of freedom and nuclear spin degrees of freedom. And it's actually very complicated and worse a Nobel Prize that Tony Leggett got in 2003 to figure out what's going on with the spin and various phases there. The problem with helium are known, so it's very complicated, as I said, very cold temperature. It's not accessible optically, and you cannot push currents through it because it's neutral. So there is we're always in a search for more robust and controllable system. And one of the examples in the condensed matter, now electronic, so where you can send current through, is strontium ruthenate. And I invite you to read this very nice and relatively short report on progress in physics of Catherine Kalin on that, who actually explains that there are some discrepancies between the experiments and between experiments and theory. And basically, the phenomenon, for example, observing chiral edges remains an elusive thing. And basically, in this context, the question is still open. So none of these things that I show here have been clearly kind of observed experimentally. And this brings me to ultra-cold gases, that it's usually very, acts very nicely when there is an important long-standing problem. Like, for example, I can say, what happens with the ordinary BCS-BEC crossover in the last 20 years. So it was completely solved by ultra-cold gases. And should also note now the ongoing progress on supersolidity in dysprosium in strongly magnetic atoms, which is being another long-standing problem, which is being solved as I speak now, basically. So what about p-waves? Why it has not yet said that word, in the p-wave business? And in order to explain that, let me remind you what is the ordinary BCS-BEC crossover. This is a phenomenon that happens in the two-component Fermi gas. I denoted by okay, spin up and spin down, or different colors here. So if you take a two-component Fermi gas and assume that you have a, you can change interaction between the components by using the Feshbach resonance. So on the so-called BCS side of the resonance, where the scattering length is negative and small, you have a weak attraction between the components. This is the BCS regime, where you have large Cooper pairs. So when you increase the scattering length and pass through a resonance to the positive side, you've seen it many times in Jean's lecture. So you have a bound state entering, and this bound state becomes a boson, composite boson. So it turns out that this BCS-BC crossover is really a crossover, a gradual change of the size of the Cooper pair into the composite boson. And it's well described by the so-called BCS type ansatz, where basically you deal with the two-body problem, and the effect of the medium is just, well, roughly is whether there are states occupied, allowed, and disallowed for these two atoms that you are dealing with. I should have added some big names here, Nozier and Leggett again, but you probably well know all this ordinary BCS-BC business. What is less known is that a similar P-wave ansatz have been written for the P-wave case when you consider spinless fermions close to a P-wave resonance. And this ansatz gives you a topological transition, not a crossover. It's a topological transition. And the topological phase is the BCS phase. Here I introduce the S. S is the P-wave scattering surface in 2D. So let's say, let me talk in the two-dimensional case. This is the analog of the scattering length. The peculiarity of this system is that the BCS pairs, they all have, these are P-wave pairs, they have angular momentum, and they all rotate in one direction. So, and the system develops the so-called macroscopic angular momentum. So we have the angular momentum is n over 2. This is the number of pairs multiplied by the unit angular momentum. And yeah, so important is that they all rotate, so they break the chiral symmetry. They should all rotate clockwise or anti-clockwise. And this is why it's called px plus ipy, or px minus ipy for the other chirality. And depending on how you look at it, you can think that this current flows on the edge of the system. So you have an edge current, and this is this thing that is elusive in these condensed matter experiments. Particularly counterintuitive is to imagine this thing to happen in the extreme limit of very weak interaction there, because it looks like it costs energy, but in fact it should be there. So in any case, this phenomenon requires an experimental observation, I think, merits some effort to explore. So currently the state of the art is, as I said, this was just a BCS type ansatz. But BCS type ansatz neglects three-body and higher order correlations. And it actually, in fact, in the P-wave case, it may not be as simple as in the S-wave case. So far, we know that the BCS theory works well in the extreme limit of very small attraction, P-wave attraction. But it also, in this case, gives an exponentially small values of the gap and critical temperature. And since we are spoiled by the BCS-BC crossover, instead of cooling the system, we tend to increase the interaction and cross the transition in this manner. We have a temptation to increase the P-wave scattering surface. But it may not work that well, because it's known that on the solution of the three-body problem it's known that close to resonance, you have trimers and something that is not described by the BCS ansatz, by the two-body problem, and fast relaxation. And experiments also showed that close to P-wave resonances, there are losses, basically, and you cannot do much with the system. So one thing that I can explain you is why this happens. I can do it in a single slide. So basically, you've seen these pictures in Jean's lectures. So here I plot the van der Waals, but this is a schematic plot of the van der Waals potential and the wave function of a weakly bound state there. So you see it has many nodes here, and then so I plot r times psi, and this is exponential, e to the power of r minus a. And when a is larger than the van der Waals range, there is a large region where there is a linear kind of slope. So there is no difference between the solution at zero energy and at the energy of the at the binding energy. Okay, so this linear thing is given by this expression. This is the solution of the zero energy at zero of the radial Schrödinger equation at zero energy. So basically, there are two linearly independent solutions, one over r and constant, and the scattering length plays the role, fixes the ratio between the two. Anyway, so if you calculate the normalization integral with this wave function, you will see that it is dominated by distances of the order of a. When a goes to infinity, the normalization integral diverges, which means that particles do not spend too much time in the van der Waals region, in the region given by the van der Waals range. And we call it extended pair and halo state because they spend most of the time in the classically forbidden region. The situation is different with the p-wave resonance because we have to take into account when we write down the radial Schrödinger equation, we add the centrifugal barrier there. And this changes the behavior of the wave function, even at zero temp. Yeah, by the way, so at zero energy, there are two solutions, one over r squared and r, different from the S wave case. And the proportionality coefficient there is called p-wave scattering volume in 3D. And since I'm going to talk about 2D, there is also, I just show you what happens in 2D. So it's 1 over rho minus rho, and S is the p-wave scattering surface. In all cases, because of the centrifugal barrier, there is not much difference when you cross the threshold, when your energy of the bound state crosses the threshold. Because of the algebraic decay here, the normalization integral converges and particles spend most of the time inside the potential, behind the barrier. The situation is a little bit better in 2D because the normalization integral diverges logarithmically. This has been noticed by Jesper Levinson, Nigel Cooper, and Victor Gurari in PRA in 2008. But it's not a drastic kind of it's not a drastic change there. So what happens with the system is that since two particles are close by, the third one comes in and leads to a relaxation or recombination to a deeply bound state. And they don't care about the Pauli exclusion principle here because the energies are so high that they don't, it's not quantum anymore, this problem. Okay, maybe I'm simplifying a little bit because the tail, this algebraic tail, it does contribute, but not the way we like. So it actually contributes to a three-body repulsion, to a three-body attraction, and it actually increases the recombination rate. And to finish this, by contrast, in the S-wave case, so we have very extended molecules, and when they in order to relax, they need a third particle. Let's say if I consider this triple here. So the point is that the identical fermions do not interact with each other, and yet they have all three together from distances of the order of A, large distances, to distances of the order of the van der Waals range. And this is suppressed because two of them are identical. It does not matter what I take. In the two-component gas, any triple will contain at least two identical fermions. And since these fermions do not interact, there is no p-wave resonance like here. So this relaxation is suppressed. Okay, so what do we do about it? The idea is that to pass from the p-wave resonance situation where you have a p-wave resonance at short distances, to a situation like this, where the short range kind of interaction is non-resonant. So you basically consider non-interacting fermions, but you somehow organize or engineer a long range attraction between them. And important thing is that if this attraction, if you have a bound state, there is only one bound state here. There are no deep bound states where these two particles can go into this potential well. Okay, so in the sense, it's like an artificial helium-3. There are many problems with helium-3, but there are no relaxation to deeply bound states because there is only one, or maybe not even one state there. Okay, so in this sense, we want to obtain an artificial helium-3. Many proposals, many theoretical works implicitly or explicitly use this idea. For example, they use these long-range interactions to induce P-wave superfluidity, or a much more wealthier kind of a layer of literature deals with induced interactions, where you have non-interacting fermions immersed in a bath of bosons or fermions, and there is an induced interaction because of the exchange of phonons or particle Hall excitation in the host gas. Okay, so finally, our proposal is yet another version of this thing. We just decided that let each fermion carry a boson with it. So we have instead of considering fermion, let's say these yellow guys are fermions. So each one carries a boson with it and interact with another. So Fermi-Bose molecule. So this Fermi-Bose molecule is a fermion and interacts with another Fermi-Bose molecule by exchange of bosons. So I will explain where this P-wave attraction mechanism comes from. And most of our work is basically to discuss various inelastic processes in the system and to exclude them from the consideration or to prohibit them energetically and things like this. And also an important, okay, as far as we understand, the important achievement of this is that we can do a decent P-wave attraction for in the isotopic mixtures, which is important from the technological viewpoint, because it's much easier to work with isotopic mixture than with the heteronuclear one. Okay, so this P-wave attraction mechanism. The story starts with this, the so-called universal trimer described by Kartavtsev and Malich. So it happens in a system of heavy fermions, identical fermions, and a light atom. Assuming that light atom is bound to a heavy atom in the S-wave manner, so it forms an S-wave bound state at some large scattering length with a heavy one. It turns out that in this system, when the mass ratio is larger than 8.2, you have a bound state with L equals 1. And this is the picture, original picture of Kartavtsev and Malich from the original paper. Here is the mass ratio, and this is the energy of the trimer. So you see, this is the atom dimer threshold, and it appears at 8.2, and then it becomes deeper bound. There is actually another trimer state there, which we're not interested here. When the mass ratio is below 8.2, so here, this atom dimer, okay, this trimer state becomes a P-wave resonance, attraction between atom and a dimer in the P-wave channel. And this attraction has been observed in the case of potassium-lithium scattering. The mass ratio is 6.6, yes, quite a bit below the critical mass ratio here. And the attraction is strong, it is visible and strong, and not accompanied by losses. This is the important thing, that we have a system with P-wave attractive interaction not accompanied by losses. And the idea is that I have just explained, because particles actually do not approach each other to distances of the order of von der Waals potential, but all this P-wave attraction happens at distances much larger than this. And the last ingredient is that if you go from 3D to 2D, this critical mass ratio changes to 3.3. That was found by Ludovic Prikopenko and Paolo Pedri in 2010. Okay, so in order to describe that, I would like to, in order to proceed with our problem, I would like to stop a little bit and describe the mechanism behind this attraction there. And this is what I will do in the Born-Oppenheimer approximation, because it's nice for explanation, although all calculations we do exactly, not assuming any adiabatic approximation. So in the Born-Oppenheimer approximation, you fix two heavy atoms and you allow the light atom to be in the ground state, and you measure its energy as a function of the distance between the heavy atoms. So this is the plot of this energy. This energy is then used as a potential energy surface for the heavy, when you solve the problem for the heavy atoms. Okay, so the feature is the following. When the distance between the heavy atoms is much larger than the scattering length, than the size of the dimer, this thing asymptotes to the binding energy of the dimer, reasonably. When the distance becomes much smaller than the scattering length, the scattering length falls, drops out of the problem, and the effective potential is scaleless. It's 1 over r squared with this coefficient. And you can change it by changing the mass of the light atom, because, of course, the light atom here has a mass, and it's its energy that we're counting. Now, when I solve the problem, the Schrödinger equation for the heavy particles, I should add the centrifugal barrier there, because these are identical fermions. I should take into account the quantum statistics there. So with L equals 1, so the lowest possible centrifugal barrier. It turns out that when you sum up this exchange potential and the centrifugal barrier, both monotonic functions, you end up with something which is not monotonic. So these are the, yes, so I forgot to say that centrifugal barrier, of course, comes with the mass of the heavy atom. So when you sum them, the mass ratio plays a role and changes the shape of this curve. So when the mass ratio is small, of the order of 1, let's say, the centrifugal barrier wins because of this factor 0.16, you see there. It's a numerically small number. And we basically have, as if particles do not interact, kind of, the Pauli exclusion plays a role there. When we increase the mass ratio, this is the black curve is for the lithium potassium, which was, I worked a lot on lithium potassium, that's why, I used to show this thing. You see, it develops a minimum here, but it's not enough to bind it's not enough for a trimer state, but it is a scattering, it gives you a scattering resonance at finite collision energy. And the red curve is for 8.2. This is where you start to have a bound state in this potential well here. And finally, when the mass ratio is larger than 13.6, this is the Efimovian case, where the system does not even have a repulsive 1 over r squared barrier here. We're interested in mass ratios smaller than that. And for these mass ratios, this repulsive barrier is actually good for lifetime, because it does not allow particles to approach to distances to the van der Waals range. So it's important and it's nice to have it. So this is the potential that I showed you on the previous slide, and van der Waals range would be here at small, tiny distance. Okay, so concerning the difference between 3D and 2D. So in 3D, what we did, we took the effective potential. So I shifted by the dimer energy. But anyway, so this is the induced potential, and this is the centrifugal barrier. Okay. For L equals 1, we have a critical mass ratio 8.2. In 2D, okay, so the induced potential is a little bit different, but we can imagine, for example, the situation where heavy particles are in the plane and the light atom is in 3D. So the so-called mixed dimensional situation where the induced potential is the same as in 3D, but the centrifugal barrier is different. It's two-dimensional one, L squared minus 1/4. But in fact, even if the light atom is in 2D, these induced potentials are not very different from each other. Different, but not much. And therefore, we can estimate by if you follow my logic, you can now estimate what mass ratio is needed to bind the trimer in 2D. And I just take the three-dimensional one and multiply by the ratio between the centrifugal barriers, and I get 3.1, whereas the exact number is 3.3. So you see, it's actually quite nice, this scaling. And we can conclude that the centrifugal force is weak in 2D, so you need smaller mass ratio to bind. Okay. Second thing, what do we have two light bosons? See, I slowly approaching to my Fermi-Bose problem. If we have two light bosons, let's assume that they do not interact with each other. The induced, so I put both into the ground state, into this Gerade-bound state, and this effectively multiplies the induced potential by a factor of 2, which means that the critical mass ratio to form this time a tetramer decreases by a factor of 2. So in 2D, we arrive to a situation where we expect a P-wave resonance to be at mass ratios close to 1, between 1 and 1.5. And yes, so this is a feature of the two-dimensional case. So we've checked this hypothesis because, you know, it's based on the Barnum-Benheimer approximation, but with the exact calculations. These are the parameters of our calculations. We have MF, MB, the masses of atoms. Interaction between Bose-Fermi interaction is characterized by the scattering length, AFB. And then we'll also introduce the Bose-Bose interaction, assumed to be repulsive and weak. Okay, so this is what the definition of S, or if you want, it's better to use the effective range expansion for the P-wave, two-dimensional P-wave case, which goes like this. It has two parameters, the scattering surface and the effective range. And we actually do not solve the scattering problem. We solve we solve for the energy of 4 particles in a parabolic potential, and we use the formula of Doherty-Blume how to get from the energy from the spectrum of the system in the parabolic potential to the scattering parameters, to the scattering surface. And this is the result of our calculations for 2 different mass ratios, 1 and 2. For the mass ratio 2, we see a tetramer state. So here I plot 1 over S as a function of the ratio between the scattering length, Bose-Bose and Fermi-Bose scattering length. So we see that when the Bose repulsion, so there is no repulsion, we have a tetramer state in both cases actually, where S is positive. This means that like scattering length is positive, you have a bound state. Positive S means you have a bound state, and bound state for us is a tetramer state. So for mass ratio 2, we indeed see a tetramer state, which is pushed above the dimer-dimer threshold by Bose-Bose repulsion. And relatively weak Bose-Bose repulsion pushes the tetramer in the equal mass case also to the attractive dimer-dimer side. And this is actually what we want. We don't want a tetramer, we want a P-wave attractive potential to stay on the topologically non-trivial side on the BCS side of the resonance. Okay, is the story over? No, the story is not over, because we have to worry about and why we need Bose-Bose repulsion. I will explain you. So unfortunately, this system can experience chemical reactions. So two dimers can form a trimer and can recombine into a trimer and an atom. And these are just and three dimers can do more complicated clusters like this. And here I show only the dangerous processes. Of course, these are Bose rich. Okay, yellow guys are bosons, and this guy is a fermion. So these are all Bose rich clusters. There are we found no Fermi rich clusters there. So there are only some dangerous ones that I show here. And okay, so this graph shows you the energy of different clusters. So FBB is this one, FBB, and FBBB is this one, and FFBBB is this one. Okay, in the two cases, when mass ratio is 1 and mass ratio is 2. Okay, first thing that I should mention is that this is the tetramer that I showed you on the previous slide. So this is FFBB tetramer, which goes through the dimer-dimer threshold, which is -2 here at this ratio of the order of 10 to the -5. Here we don't have a tetramer. It's on the left, to the left of this point. So to analyze, for instance, the stability of the system with respect to this trimer formation here, we have to calculate the energy of the trimer and compare it with the two energies of the dimer. And we see that when Bose-Bose interaction is repulsive, okay, sufficiently repulsive, we get it above the two dimer threshold, which means that this reaction is energetically forbidden. Okay, on this in the three dimer sector, we have to worry. We've figured out that we have to worry about this FBBB cluster, which goes through the three dimer threshold only when Bose-Bose interaction is sufficiently strong. It's stronger than, okay, this ratio should be larger than 10 to the -5. Surprisingly, in both cases, it's like this. I don't know why it happens, but it's probably a coincidence. So where do we stand now is that at least from the three dimer, for three dimers, everything is elastic if the ratio of Bose-Bose to Fermi-Bose interaction is 10 to the -5. Okay, so this is in this plot we are kind of on the right of this on this side. And now we can dream about some many body applications. So we can, for example, consider a gas of these two-dimensional dimers, if you want, with distance between them of the order of their size. So it's like in the spirit of artificial helium-3, okay? And if the mass ratio is 2, we can even reach the resonance. And even in the isotopic case, we have a decent value of S of the order of minus square AFB squared, which gives at least on the paper, it gives a decent gap parameter and critical temperature of the order of the Fermi energy. Okay, so okay, this was in pure two-dimensional model, right? So we have to, if we want to be practical, we have to propose a quasi two-dimensional model. So we pick up potassium 40, potassium 39. We know the formulas how to get from three-dimensional scattering length to two-dimensional ones for FB and BB. And we can look, we can search for a nice resonance there. Indeed, there is a resonance in 3939, Bose-Bose resonance, close to the 26, close to 26 Gauss, which is with the width of the order of half a Gauss. And near this field, Fermi-Bose scattering length is minus 20 nanometers, thanks to Andrea Simoni, who showed me this number. And for example, we can tune the Bose-Bose scattering length as we like, and we need something about 7 nanometers plus or minus, I don't know, 1 nanometer. And if we squeeze the system with the confinement of 40 nanometers, we obtain Fermi-Bose molecule of 1 micron size, and ABB over AFB 7 times 10 to the minus 5. Okay, so yeah, so talking with experimentalists, for instance, with Laetitia Taruel, with whom we discuss a lot this proposal, she says that actually this background scattering length, which is minus 33, is not very nice because she does not know how to prepare the BEC there. But she is smart. I think she will find a way, either another resonance or maybe work with this resonance, but I don't know, use some other procedure to prepare BEC. Okay. Am I doing time? Yes. Okay. So, and the last, but very important, but maybe technical point is the relaxation in this FBB channel. This is the relaxation to the van der Waals states. We have to be kind of realistic and think about this one. So it's not a creation of clusters, but it is like it's counting the probability that 3 atoms, 2 bosons, because in the Fermi-Bose channel there is a Pauli exclusion there. So what is not Pauli excluded is this BBF channel. So the 3 atoms can approach each other to distances of the order of van der Waals range and can recombine, and this will lead to losses. In order to estimate the rate of this, let's assume that we have closely packed molecules in 3D, okay? And let's further assume that they do not interact, so there is no interaction between the atoms. In this case, the probability to see 3 atoms close to each other scales like van der Waals range to the size of the molecule cube. This is the probability to have 1 boson on top of 1 fermion, well, not on top, but in the region given by R van der Waals. And then the other one will also produce this probability. And the relaxation rate is then we multiply this probability by this intrinsic rate, this van der Waals rate. And we end up with this formula here. Unfortunately, when we introduce resonant FB interactions, this is the solution of the 3-body problem. But instead of the constant hyperradial wave function, we have to put rho to the -2. Rho is the hyperradius. And this eventually increases the relaxation rate, and it makes it comparable to the binding energy of the molecule. So this is bad because you know, the molecules do not leave as long as the oscillation, you know, back and forth in you know. So yeah, this is bad because in 3D the system is Efimovian. But in 2D we do the same. I just skip this. We do the same, and we end up with the suppression factor, which is the oscillator length divided by the size of the molecule, quasi-2D molecule squared. And in the example that I showed you, this was 40 nanometers, and this was 1 micron. So here we have a 2 orders of magnitude suppression. And you can also, you know, play with it. You can squeeze it more, and you can make a bigger molecule if you like. And physical explanation of this suppression is that in 2D, it's the same why in 2D there is no Yefimov and Thomas effect. So apparently, strong 2-body interaction in 2D does not lead to this enhancement, Efimovian enhancement of 3-body correlator in 2D, and we have to use that because basically, you know, it is surprising that 2 systems, 3D and 2D, from the 2-body viewpoint, as strongly interacting, you know, similarly strongly interacting, they are so different from the viewpoint of short-range 3-body physics. Okay, so I wanted to mention related activities in the end. So yeah, as I showed you before, so there is this induced P-wave superfluidity, the line of research which is pursued by Georg Brun and some other people there, but I just wanted to let you know that it exists. I would also like to mention this work in the Polish team on self-bound Fermi-Bose liquids, Fermi-Bose droplets. So here I wanted to say a few words. Remember that I told you that I was worried about this process where a few dimers can form a cluster, Bose-rich cluster. So for example, you have what I showed you is like 3 dimers, they form F2B3 cluster. Okay, but in principle, there can be 7 dimers can form 6F7B cluster, which we were not capable of calculating because there are too many particles there. But in principle, it's possible. But on the other hand, maybe it's not that bad, because if you look at this cluster as 6 dimers bound together by a boson. Okay, well, boson is there, but you can still think about these dimers as fermions with p-wave attraction, and maybe, you know, the phenomena that we are after, this p-wave superfluidity is there in this cluster. So you see, and this work that this Polish team has done is kind of parallel and complementary to what we're doing. So maybe we should just continue this studies of self-bound Fermi-Bose liquids. And yes, at the time we were doing this from the few body side, we were inspired by this work of Pascal Nedon on heavy light bosonic tetramers. Okay, so as a summary, okay, if there are experimentalists in the audience, I hope that I convinced you to stop everything that you are doing now and try to do, you know, Fermi-Bose molecules, try to follow our proposal. And we kind of did some preparatory work. So we say that it should be in quasi-2D because of the lifetime and because of the favorable mass ratio scaling of the p-wave attraction in this case. Very promising candidate is potassium, but it can also be dysprosium, two isotopes of dysprosium. And I didn't mention, but for the mass ratio equals 2, for example, potassium sodium would also be possible. Potassium 40, sodium 23, it's almost 2 mass ratio 2. But people who are doing potassium sodium, they're busy with ultra cold molecules business. So I just have to wait a little bit till they stop doing that. Okay, and as an outlook, okay, so now since we have calculated the dimer scattering properties, we can actually integrate out the internal kind of degree of freedom and replace them by elementary fermions with proper 2-body parameters like S and the effective range. Let's say Gaussian potential, for example, and we can now continue, let's say, calculate a 7-body problem of fermions in a trap and see what's going on with this p-wave. I mean, what is the consequences of this p-wave attraction there? Okay, with this, I thank you for your attention.